the factory that builds the machines building everything else. So you want to own an industrial robot factory. Imagine owning a factory where the products coming off the production line aren't cars, refrigerators, or smartphones. They're machines that build those products. Robotic arms weld vehicle bodies. Automated systems move components. Precision robots assemble electronics. Machines inspect products. And industrial robots are increasingly becoming the physical workforce behind modern manufacturing. Now imagine being the company that manufactures those robots. Instead of selling one finished product directly to consumers, you're selling the machines that other businesses use to manufacture thousands or even millions of products. That sounds like an incredible business. And it can be. But industrial robotics is an expensive and highly competitive industry. A robot isn't simply a metal arm with a motor. Inside are precision gearboxes, servo motors, controllers, sensors, cables, software, safety systems, and thousands of carefully engineered components. And before a single robot is sold, the manufacturer may spend years developing the technology. And that means the real money is in precision, reliability, engineering, scale, and long-term relationships with industrial customers. So what does it actually cost to build this business? Let's break it down. The economics of an industrial robot factory are different from almost any normal factory. You're not just manufacturing hardware. You're manufacturing automation itself. Which industrial robot factory are you buying? Let's imagine we're building a large industrial robotics manufacturing facility capable of producing 50,000 robots per year. That's a substantial operation. The factory would need precision machining equipment, CNC machines, motor assembly stations, gearbox manufacturing, electronic testing equipment, robot arm assembly lines, paint and finishing systems, software testing laboratories, quality control facilities, warehouses, and specialized engineering areas. But there's something different about this factory. The robots themselves don't all have to be identical. A customer might need a 6-axis robotic arm for welding. Another might need a smaller robot for electronics assembly. Another might need a heavy-duty robot capable of moving large components. So the factory needs flexibility. It has to manufacture different configurations while maintaining extremely tight quality standards. You're not building a factory that produces one simple product millions of times. You're building a factory capable of producing thousands of variations of an extremely complex machine. The first $1 billion. Now imagine building the entire operation requires approximately $1 billion. The actual investment could be significantly higher or lower depending on production capacity, location, vertical integration, automation, and how many components are manufactured internally. But $1 billion gives us a useful model. That money goes into the building, precision machinery, CNC equipment, assembly systems, electronics laboratories, testing equipment, warehouses, research facilities, software infrastructure, and production tooling. Then comes another major expense: research and development. Industrial robotics is a technology business. The company has to continuously improve motors, controllers, gearboxes, sensors, software, motion control, artificial intelligence, safety systems, and energy efficiency. Imagine spending $200 million every year on research and development. That sounds enormous. But if the company sells tens of thousands of robots every year, the cost can be spread across every unit. In industrial robotics, the factory is only half the investment. The other half is the engineering knowledge required to make the machine competitive, from raw materials to a finished robot. Now production begins. Steel and aluminum enter the factory. Precision machines cut and shape structural components. Robot arms are manufactured. Joints are machined. Gear systems are prepared. Servo motors are assembled. Sensors are installed. Cables are routed. Controllers are connected. And software is loaded into the system. Then comes calibration. The robot has to know exactly where its joints are. It needs to move with precision. It needs to repeat the same motion thousands of times. And it needs to communicate with other machines. A robot that is off by a few millimeters may not sound like a major problem, but in automotive or electronics manufacturing, that error can destroy an entire production process. The value of an industrial robot isn't how far its arm can move. It's how precisely and reliably it can repeat that movement thousands of times. That's what customers are paying for. The motor and actuator cost problem. One of the most important parts of an industrial robot is the actuator system. The actuator creates movement. That requires motors, gear systems, drives, bearings, and control electronics. A 6-axis robot can require multiple high-performance servo systems, and those components have to work together with extraordinary precision. Imagine the average robot contains $5,000 worth of motors, gearboxes, and actuator components. At 50,000 robots per year, that's approximately $250 million worth of these components. Now imagine a manufacturer can reduce that cost by just 10%. That's potentially $25 million in annual savings. But designing cheaper components without reducing reliability is difficult. Industrial customers don't want a robot that saves money upfront but fails repeatedly. In industrial robotics, the cheapest machine isn't necessarily the most valuable machine. The valuable machine is the one that keeps working. The electronics and sensor problem. Modern industrial robots are also computers with arms. They need controllers, sensors, encoders, communication systems, power electronics, safety systems, and specialized processors. Sensors tell the robot where its joints are. Controllers calculate movement. Encoders measure position. Safety systems detect potential hazards, and software coordinates the entire operation. Imagine electronics and sensors represent $4,000 of the manufacturing cost per robot. Across 50,000 robots, that's another $200 million flowing through the supply chain every year. And electronics can introduce another problem. Technology changes quickly. A controller that was considered advanced 5 years ago may become outdated. The robot may be made of steel, but a growing part of its value comes from electronics and software. That means robot manufacturers increasingly have to operate like technology companies. The cost inside every robot. Now let's build a simplified economic model. Imagine the factory produces 50,000 industrial robots per year. Suppose the average selling price is $35,000 per robot. That would create approximately $1.75 billion in annual revenue. But the factory doesn't keep $35,000 from every robot. Materials cost money. Motors cost money. Electronics cost money. Labor costs money. Engineering costs money. Testing costs money. Transportation costs money. And customer support costs money. Suppose the average manufacturing cost is approximately $22,000 per robot. At 50,000 units, that's approximately $1.1 billion in manufacturing costs. That leaves roughly $650 million before additional operating expenses. A robot selling for $35,000 doesn't mean the manufacturer makes $13,000 of profit. The real margin appears only after every cost has been paid. The final profit can be dramatically smaller. The automation advantage. Here's the fascinating part. The robot factory itself can use robots. Automated machines can move components. Robotic systems can perform repetitive assembly. Vision systems can inspect parts. Automated warehouses can manage inventory. And software can monitor production. This creates a feedback loop. The factory manufactures robots. Those robots improve the factory. The improved factory reduces production costs. Lower costs improve robot margins. And stronger margins can fund more investment in automation. The factory that sells automation can also use automation to make its own products. That creates a powerful economic advantage. The labor and engineering problem. But robots don't eliminate human workers from the factory. They change the type of workers required. The company needs mechanical engineers, electrical engineers, software developers, robotics engineers, technicians, quality control specialists, machine operators, maintenance teams, and production managers. These employees can be expensive. Imagine the factory spends $250 million per year on labor and engineering-related costs. At 50,000 robots, that's approximately $5,000 per robot. That is a significant part of the economics, but highly skilled employees can also create enormous value. A better engineer can improve a product. A better production process can save millions. A better software system can improve every robot the company sells. In robotics manufacturing, human expertise isn't being replaced. It's becoming more specialized. The production volume gain. Now imagine the factory has massive fixed costs, buildings, machinery, R&D facilities, testing equipment, management, software, and engineering infrastructure. Suppose fixed operating costs are approximately $500 million per year. At 50,000 robots, that's $10,000 of fixed cost per robot. But what happens if production increases to 75,000 robots? The same fixed costs are now spread across more units. $500 million divided by 75,000 equals roughly $6,667 per robot. That's a dramatic improvement. This is why scale matters so much in industrial robotics. The more robots you produce, the more efficiently you can spread fixed costs. The capacity utilization shock. Now, imagine the opposite. The factory was designed for 50,000 robots, but customers only order 30,000. The company buys fewer components. Some labor costs decline, but the building remains. The machinery remains, the R&D department remains, the management structure remains, and the equipment still needs maintenance. If fixed costs are $500 million, producing 30,000 robots means those costs become approximately $16,667 per robot. Suddenly, each machine becomes dramatically more expensive to produce. An industrial robot factory doesn't need just technology. It needs enough demand to keep that technology economically productive. The supply chain problem. A robot factory depends on thousands of components: motors, bearings, gearboxes, sensors, controllers, cables, semiconductors, steel, aluminum, power electronics, and specialized components. One missing part can stop production. Imagine the factory has 10,000 motors ready, thousands of robot frames prepared, but a specific controller isn't available. Those robots may remain unfinished. Inventory starts building, production schedules are disrupted, and customer deliveries can be delayed. The most expensive component in a robot factory can sometimes be the component you don't have, because without it, every other component may simply sit on a shelf. The customer problem. Now here's another challenge. Industrial robots are not impulse purchases. A factory customer may spend millions of dollars on an automated production system. That means customers carefully evaluate the technology. They compare prices, performance, reliability, integration, maintenance, software, and long-term support. A robot manufacturer, therefore, isn't simply selling hardware. It is selling a long-term industrial relationship. If a customer installs thousands of robots, replacing them later can be extremely expensive. That creates an opportunity for recurring business, maintenance, software, replacement parts, upgrades, and additional robots. The first robot sale can be valuable, but the customer relationship can be worth much more over the machine's entire lifetime. The integration problem. Another major expense is integration. A robot rarely works completely alone. It may need to communicate with conveyors, cameras, welding equipment, machine tools, sensors, production software, and safety systems. Customers may therefore need engineers to integrate the robot into their factory. That creates additional costs, but it also creates additional revenue opportunities. Robot manufacturers can sell installation, programming, consulting, maintenance, training, and software. The robot itself may be the product, But the entire automation system is where the larger business opportunity can appear. The technology problem. Industrial robotics is evolving rapidly. Traditional robotic arms are becoming more intelligent. Vision systems are improving. Artificial intelligence is becoming more useful in manufacturing. Collaborative robots are expanding automation into areas previously difficult to automate. And software is becoming more important. That creates both opportunity and risk. A company that develops a breakthrough technology can capture new customers, but a company that misses a major technology shift can quickly fall behind. In robotics, yesterday's breakthrough can become tomorrow's standard feature. That means manufacturers must keep investing. The inventory trap. Now imagine the factory has $300 million worth of components and finished robots sitting in inventory. That's a lot of money tied up. If demand changes, some models may become harder to sell. If technology changes, certain components may become outdated. And unlike basic raw materials, highly specialized robot components may have limited alternative uses. That makes inventory management extremely important. Too little inventory can stop production. Too much inventory can trap millions of dollars in cash. The best factory constantly balances both risks. The ownership traps. The first trap is assuming automation automatically means high profits. The second is underestimating R&D expenses. The third is producing more robots than customers need. The fourth is relying too heavily on one major industry. The fifth is ignoring software. The sixth is underestimating integration costs. The seventh is carrying too much specialized inventory. The eighth is failing to keep up with new robotics technology. The ninth is competing only on price. And the final trap is thinking the robot itself is the entire business. The strongest robotics companies don't just sell machines. They build ecosystems around those machines. The factory verdict. So what separates a profitable industrial robot factory from a billion-dollar manufacturing experiment? Precision, scale, reliable components, strong engineering, high production volume, efficient automation, continuous research, and long-term customer relationships. The smart owner doesn't simply ask, how many robots can we manufacture? They ask, how much does each robot cost? How much does R&D add to the cost? How much capacity do we actually need? How quickly is the technology changing? How much revenue can each customer generate over the robot's lifetime? And how much profit remains after manufacturing, engineering, software, service, and support? Those are the numbers that determine whether the factory succeeds. The real economics. From the outside, an industrial robot factory looks like a place where machines build machines. But economically, it's something much bigger. It's a business selling productivity. A car manufacturer buys robots because they can help build cars faster. An electronics manufacturer buys robots because they can improve precision. A warehouse buys automation because it can reduce repetitive labor. And a manufacturer may keep buying robots as its production expands. That creates a powerful economic model. The robot is sold once, but the relationship can continue for years. Maintenance generates revenue. Software generates revenue. Replacement parts generate revenue. Upgrades generate revenue. And new production lines create additional demand. The most valuable thing an industrial robot factory produces isn't the robot. It's the productivity that the robot creates for the customer. That's why the economics can be so powerful. But the risks are just as real. If demand falls, capacity becomes expensive. If R&D spending gets out of control, margins disappear. If technology changes too quickly, yesterday's machines become outdated. If supply chains break, production stops. And if competitors offer better robots at lower prices, customers can move. So is owning an industrial robot factory a license to print money? Not exactly. It's a massive investment in engineering, manufacturing, software, and industrial technology. If the factory achieves high production volume, controls costs, develops valuable technology, and builds long-term relationships with customers, the returns can be extremely attractive. But if the factory produces too much, loses technological leadership, or fails to generate enough demand, those expensive machines can quickly become an enormous financial burden. The most dangerous robot factory isn't the one that can't build enough robots. It's the one that can build thousands of them, but can't make them valuable enough to justify the billions invested in the technology behind them. That is the real economics of owning an industrial robot factory.